Hi everyone, welcome back to the channel. In this video, I want to go over my journey of running this, a 3DFX Voodoo 2 3D accelerator from 1998. On that, a Raspberry Pi 5 ARM64 single board computer that was released 25 years later. Let's get to it. First thing to go over is, why would you even want to do that? And although I'm a firm believer that because I can is a perfectly valid answer, in this case there is a bit more to it. So let me tell you a little story. I promise I'll try to be quick. Back in the late 1990s, I was a teenager and I owned 3DFX cards. First a Voodoo 1 and then a Voodoo 2. And I still remember that I wanted to learn how to program those cards. This was way before we had unified and standard graphics API for consumer cards. So I had to look into 3DFX's own API, Glide. The internet also wasn't as widespread as it is today, and I certainly didn't have any kind of broadband access to it, and my English wasn't all that great either. All of that to say that finding information and help was not as easy as it is today. I don't remember exactly how far I got. I think maybe drawing a couple of colorful triangles, but that was about it. And so with all the retro computing stuff going on these last few years, I always had this idea in the back of my mind of trying to program that vintage hardware, either using the original API or even bare metal, programming registers directly. This brings us to now. With summer coming up, I decided to do a bit of spring cleaning and try to find new homes for all the tech stuff I'm not using rather than e-wasting them. That led me to eBay, and the inevitable happened. Instead of getting rid of some of my tech gadgets, I ended up buying new ones. In my defense, those Voodoo 2 can go for several €100, and this one was still at a decent price, with time almost up. So I placed a last-minute bid, and I didn't think it would win, but it did. A week or so later, the parcel showed up, and I was now faced with the problem of testing it. My first idea was to use this, Circris Net 4501. It's a fairly old single board computer, mostly targeted at firewall appliances and such, but it has a x86 CPU and a PCI port. That unfortunately didn't pan out. Its PCI port is 3.3 volt and the Voodoo 2 is not a universal card. It's keyed for 5 volt PCI slots only. I don't have any other systems with PCI slots, and I didn't really want to get one either. So I turned to these. These are PCI Express to PCI bridges. And simply put, they allow you to connect a PCI card into a system that only has PCI Express ports. I have two different models here. One is based on the AS Media ASM 1083 chip, and one is based on the Pericom PI7C9X111SL. I will focus mainly on my experience with the former, the ASM one, since that's the one I tried first. After the fact, I also did a quick search and found another video of someone using a Voodoo 2 on a modern x86 PC using what looks like the exact same adapter. No, all I needed was a PCIe port to plug it in. My laptop has Thunderbolt, but I don't have all the required cabling and adapters to get a real PCI Express port out of it, so not an option. My main desktop workstation has PCIe, of course, but they're all used up and it's pretty crammed in there, so not an option either. My NAS local server is also x86 based, but I don't want to mess with it just for random experiments. That's out too. I do have an upsquare too many PC where I hacked up an internal M2 slot to one of those USB 3 to PCIe adapter that's usually used for mining. My hope for this system was to use it exactly for this kind of purpose, where I need to run some PCIe experiments. Unfortunately, that didn't really work out, and I could never get it to work reliably, and especially not with the PCIe to PCI bridge. I also have a dedicated test system I used for work stuff. It's not very convenient or movable, and I don't want to mess with it too much, but that was an option at least, and I did end up running a couple of tests on it. We'll come to that later. And finally, I have a Raspberry Pi 5 with a PCIe adapter that gives me real PCI Express port. That's small and convenient, so I figured it would be neat to try and use it to run a Voodoo 2, because why go for simple when you can make your life 10 times harder? So there you go. that's the little story of why I ended up here. Now we can finally get to the more interesting part, the testing. This is my test setup. You can see the Raspberry Pi 5 with a PCIe slot card from 52pi.com. I plugged a PCIe extension riser cable in it just to make things a bit more stable. That goes into the ASM 1083 PCIe to PCI bridge, and finally into the Voodoo 2. I don't have anything plugged into the video input of the Voodoo 2 since I don't have any VGA to D card here. And so the output of the Voodoo 2 is just directly plugged into a monitor with a VGA input. First thing was just to check if the card was detected at all, and that went without a hitch. Just the normal configuration to enable the PCIe on the Raspberry Pi 5, and it showed up in LSPCI. Not surprising, but still reassuring. After all, this is a card from eBay. Sure, it was sold as working, but you never know. While we're looking into the LSPCI result, it's a good moment to discuss exactly how the Voodoo 2 is controlled over PCI. Over the years, the technical documentation became available, and what you can see is that the Voodoo 2 is a pretty simple PCI device. It only exposes a single 16 megabyte bar for memory mapped I/O, so from a PCI transaction standpoint, only configuration requests and memory requests are needed. Having no I/O ports is good news, because those can be a problem on the Raspberry Pi. It's also not a busmaster, so no DMA to worry about. All of that bodes very well for this experiment. When I was trying to figure out what to test next, I saw that the SST-FB module was still present in the Linux kernel tree. And this particular module is a framebuffer driver allowing to use 3DFX Voodoo 1 and 2 as raw framebuffer device in Linux. It was written back in 2000 or so, but has remained in the kernel since and kept in working condition. It's not built by default for ARM, but it was pretty easy to build it out of tree. Let me load the module and adjust the VT bindings, and what do you know? It works. Sort of. The card gets detected, the RAM DAC identified, the video signal starts, and the frame buffer shows up. For normal text console use, I also didn't really notice anything wrong at first. However, when I tried a couple of image viewers, some artifacts were apparent. Same thing appeared when I tried Emulator with direct frame buffer output. It manifests itself as missing writes, like some of the access ended up lost somewhere. Adding some delays when copying data to the frame buffer device can actually mitigate the problem, but this is not a good sign. I repeated the same test on an x86 host. Forgive me the slightly janky setup here, this is the only x86 machine I could easily use for this test. Turns out that on x86, the SST-FB module is even built and installed by default, at least on Ubuntu. I tested both image viewers and also Emulator, and these worked perfectly. No visible artifacts whatsoever. So obviously something is a bit fucked up on the Pi 5. I'm not sure if it's Raspberry Pi specific or ARM64 or exactly where this is coming from. I checked the driver and even contacted its original author, but it all looks fine to me. I'll leave it at that for now. We'll circle back to what might be wrong on later when we have more data points. The next thing I tried was the official Glide driver from back in the days. It existed for Linux and it's open source, so maybe it would work as is on ARM64. Yeah, no, it doesn't quite work that way. The driver is composed of two parts, a small kernel module and then a user space library that's doing most of the work. Let's start with the kernel module. Although it's possible to get it to build fairly easily, even on modern 64-bit kernel, it's not really doing any good. The code is a bit of a mess because of all the ifdef to handle different obsolete kernel versions, making it hard to read. It's not using any of the newer APIs for the card device. It's also missing some critical initialization, like calling PCI enable to actually request the device to be enabled first. That might not have been needed in the past, but now it sure is. It also has a weird interface to user space, exposing all the cards in the systems under a single character device, /dev/2dfx, and then using their physical base address to select which one to act on. Except that argument is 32-bit, which doesn't work so well on 64-bit systems. So all in all, I decided it would be quicker to rewrite a new kernel module presenting a slightly better interface to user space. The kernel module really doesn't do much anyway. It handles detecting the cards and then has a couple of IOCTLs to issue a few select PCI configuration requests, and it also allows to memory map the whole PCI bar into user space. I'm not even sure a kernel module is strictly necessary. I think you could get away entirely using sysfs if you wanted to. The new kernel module is up on GitHub if you want to have a look, but I suspect it might only be useful to me. The second part of the driver is the user space library. Getting it to build was not too hard, mostly disabling some x86 specific assembly code, fixing up makefiles, and also defining a custom P6 fence, memory fence macro using inline ARM64 assembly. Of course, given my new kernel module presents a different interface to user space, this part also needed some fix-up. Thankfully, that part of the user space driver was pretty isolated, and it wasn't too hard to replace their so-called fxPCI code with a custom version that deals with the new kernel interface. Their hardware abstraction layer is pretty terrible, but still, it was doable. With all that done, I could compile the glide library and the provided test and example code. But of course, it didn't work. Not even close. Digging into the code, it seems that they do a lot of row pointer math and casting pointers to 32 bits all over the place. I did my best to go around and fix all of them to use proper uint ptrt types when doing all of that arithmetic on pointer, but in the end, I couldn't get it to work. It's still crashing with a weird bus error, and I couldn't trace exactly where it comes from. In the future, I think I might try some different approach. Either making sure that the memory mapped PCI bar ends up in the lower end of the address space and fits into 32 bits, or try to identify all read and write access to the zone and give the library a fake pointer and do address translation in the methods executing the actual reads and writes. It was a bit of a bummer not being able to run Glide natively, at least for the time being. But I didn't stop there and decided to try something else. The next idea was to use some emulator, something to run DOS games, and then expose a 3dfx inside that emulator, intercept all accesses to the emulated PCI device, and redirect them to the real device. In case you're not aware, the Voodoo 2 is a pure 3D accelerator. It doesn't handle 2D at all. Back in the day, you'd have a classic 2D card, connect its VGA output to this port on the Voodoo card using a small pass-through cable, and then connect the Voodoo card output to your monitor. When not rendering 3D, the Voodoo card would be inactive and just directly pass through the signal from the 2D cards to the monitor. When the 3D game started, or at least when it wanted to switch to 3D mode, the Voodoo card would start generating its own VGA signal and send that to the monitor instead, thus completely taking over the monitor. For our purposes here, it's actually perfect because that means nothing talks to the card before starting a game, and the Glide driver built into the game will take care of the full initialization of the card from scratch. For the emulator, I picked DOSBox X. It seemed capable of running DOS games and even early Windows 95-98 games. It actually includes a full software emulation of the Voodoo 1, meaning all the code to emulate a PCI card must have been present already in it. Skipping a bit into the future, I also later had a look at 86box, a low-level x86 emulator that can more precisely emulate a lot of retro hardware, including software emulation of Voodoo 1 and Voodoo 2 cards. The codebase of 86box is actually, in my opinion, better structured than the one from DOSBox X. It also emulates systems more accurately. Unfortunately, all of that comes at a cost, and it's quite a bit slower than DOSBox X, so I didn't dig more into it and stuck with DOSBox X, although I might revisit it in the future. Given that this was just a quick experiment, I didn't bother really making a clean integration in DOSBox X. I simply ripped the guts of their software Voodoo 1 emulation, modified it to report itself as a Voodoo 2 instead, and then intercept all PCI configuration requests along with all memory mapped I/O access to the PCI bar, and redirect those to the real card through my newly written kernel driver. Let's see how that went. The test setup is similar to the previous one, but instead of a VGA screen, I now have a cable with VGA to HDMI conversion built in, going to an HDMI capture card. This is so I can use screen capture to get both what I'm typing on the Raspberry Pi and the VGA output. Also note that the emulator UI can appear a bit laggy sometimes. This is only because it's running on the Raspberry Pi and I'm forwarding the X11 connection to my laptop through SSH. So here we go. The emulator is booted. I can go into the 3dFX diagnostic tools and I can then try the Mojo diagnostic, which basically runs the initialization code and prints some info about the detected card. And it flippin' worked. With the basic test working, I was feeling bold and decided to go for broke and directly try a game. A somewhat obvious choice would be Quake, but unfortunately, although Quake itself runs in DOS, GL Quake, the variant that supports 3D acceleration, is a Windows program. So instead, I went with Tomb Raider. I definitely remember playing that with my Voodoo 1. It's a pure DOS game and it's pretty easy to find a 3dFX patched version. Here we are again in the emulator, just going into the Tomb Raider directory and starting the patched binary of the game. Now you can see the studio logo and the intro video showing up in the emulator video output because these are pre-rendered and they just output using the 2D card in the system. At this point, the Voodoo 2 is still completely idle. But then, for the menu, it gets initialized and we get this. It's a bit hard to tell, but it's basically the very first frame of the animation when the menu appears. The background is just an image and there's a few 3D items that represent each menu option that are supposed to come flying in from the back and you can barely just see them in the background. Before I dig deeper into the debug of this issue, I want to take a minute to very briefly and superficially explain how the Voodoo 2 is controlled by games. As I mentioned earlier, this early 3D accelerator doesn't use DMA at all. So the driver issues simple writes to the registers in the card address space. It basically sets up a bunch of parameters for vertex position and attributes by writing to different registers. Then writes to a special register that trigger a draw command that will cause the card to actually draw that triangle with whatever parameters were set up. And that's repeated over and over for every triangle to draw. Then there are some other special commands registers to do various operations like switching between the front and back buffer either directly or at the next vertical sync, for instance. Of course, some of those commands take some time to execute and the card can actually block the CPU if it's not ready to accept a new register write. It does have a very short hardware FIFO, so it can queue a few PCI writes, but it's not very big and the host CPU might still end up stalled trying to do more writes. As far as I understand, this is how the Voodoo 1 card operated. But here, for the Voodoo 2, they added a little trick to boost performance and make sure the CPU doesn't end up having to wait for the card too often. In the Voodoo 2, the driver can reallocate a small part of the frame buffer memory to serve as a large external command FIFO. Instead of writing directly to the control registers, the driver then writes packets requesting execution of register writes or of special commands in a special packet format inside the frame buffer memory. And then it just points the Voodoo 2 chip to look at a given address and execute the commands that have been queued there. This way, the CPU can just accumulate all the drawing commands to render a frame without ever having to wait for the card. It just needs to wait between frames to make sure it doesn't get too far ahead. And the card even has a special counter that reports how many swap buffer commands have been queued, so the game can know how many frame renders are pending already. Okay, now that we know a bit more about how the Voodoo 2 works, time to get back to the emulator and why Tomb Raider hangs. While debugging and tracing all register reads and writes, I did confirm that indeed only the first frame is being drawn. Somehow the card only executes a single swap buffer command. After looking at that for a while, I called it a day, shut everything off and resumed the next day. and that issue was now magically fixed. It didn't quite work right just yet. Sometimes it would still hang in a menu, and if it ran long enough for me to start a game, there would be graphical corruption, missing triangles and such, and at some point it would just hang. But at least it was getting past the drawing a single frame problem. What I later realized is that the card can get into some sort of bad state, and sometimes a PCI bus reset or warm reboot wouldn't always be enough to fix it. See for instance here, I purposefully crashed the card and the Mojo diagnostic tool still detects it, but you can see that some of the reported values are obviously wrong. And the 5705 shown here in decimal is 0x dead in X. I can manually issue a PCI soft reset signal, and most of the time it will be enough to bring back the card to life and working properly. See, now it identifies the card properly. But sometimes it doesn't quite work. The card would show up properly in the diagnostic tool and nothing would seem wrong, but it would only draw a single frame. And it would take a full cold reset to bring it back to a fully operational state. So with that behavior explained, let's go back to why the game is still crashing. This is how the handler for the emulated read and write to the PCI bar looks like. It's just a standard pointer dereference to whatever memory address we got from the memory map call of the kernel driver. The pointer is marked as volatile, but that's it. Next thing I tried is adding a memory barrier after all the writes, trying to make sure there isn't any funky business going on and each write actually results in a write to the real hardware in the same order. This drastically improves stability. This is what's running now, and as you can see, I can get into the game without trouble and there's much less corruption. However, it's still not 100% stable and there are still missing triangles and such. What I tried next is to copy the IORead32 and IOWrite32 functions from the kernel to make all the emulated access as safe as possible. These include some architecture-dependent ways of entering proper memory-mapped I/O operations. You can see here several blocks of ARM64 inline assembly. The result is maybe a bit better than a simple memory barrier. It's hard to tell, to be honest, and might just be random. One thing is true though, is that there are still some graphical glitches and it can still hang randomly, so it didn't fix the issue. I went and rechecked my implementation of the mmap in the kernel driver to make sure I was mapping the PCI bar into user space with all the proper attributes, and it looked fine to me. I'm using pgprod device here, which results in the same mapping attributes as what IORemap would use by default, and that's what's used inside the kernel for all MMIO access to PCI device, so it should be fine. I also tried pgprod non-cached, which is a bit more restrictive, but that didn't affect the results. On x86 machines, both these options actually result in the same mapping attributes, but on ARM64, they are a tiny bit different. If we look into the PG table header file, we can see the attribute empty device ngnrne is used for one, and empty device ngnre is used for the other. Looking at the ARM documentation, we can see what that means. The common part, ngnr, means no gather and no reorder. So transaction cannot be merged and have to be issued in order. What differs is that one allows early acknowledgement and the other one doesn't. I don't think this should make a difference here, and as far as I can tell, it doesn't have any effect on the issue at hand. The final thing I tried is to not memory map the PCI bar to user space at all. Instead, I'm using an IOCTL request to the kernel driver, and the kernel driver actually performs the read and write transaction using all the recommended kernel ways of doing MMIO access on PCI devices. You can see here the new implementation in DOSBox 6 of the read and write function for the emulated PCI device, and they issue an IOCTL for every access. And that fixed it. I can now play Tomb Raider, it doesn't crash, and there is no graphical glitches. Or at least, none that are not expected. There is sometimes some Z-buffer weirdness and some imperfect joints between triangles, but I'm pretty sure those are normal and present in the game even when running on native hardware. Now, why did this fix it? Well, I don't think it did fix anything. I think it's just hiding the problem. Going through a whole IOCTL mechanism involves user to kernel context swap and a whole lot of code, which is adding quite a bit of delay between consecutive accesses. And I think that's just masking or working around the underlying issue. Just like when adding a small delay to the framebuffer writes made the SSTFB driver work. I don't know what the underlying issue is and why it works better on x86 than ARM64. My first theory was that the modern LPAR5 could issue PCI access faster than any hardware back in the day, and this somehow messes up the hardware FIFO on the card. But this doesn't really explain why it works fine with a modern x86, which is as fast or even faster than a Raspberry Pi 5. And we know x86 works better, both because of my earlier attempt with the SST-FB framebuffer driver, and also because of a video I mentioned earlier where someone used the same PCIe to PCI bridge on a modern x86 platform and run games just fine. So my second theory is that somehow the PCIe transactions issued by the ARM64 are different. But I don't know what's different about them. And it's also not trivial to find out. Ideally, I'd monitor the raw transaction on the PCIe bus and how they get translated onto the PCI bus. But for that, I would need both a PCIe bus analyzer and a PCI bus analyzer. And I have neither. I do, however, have some idea on how to build both of those, so stay tuned and subscribe if you don't want to miss it. Another avenue I explored is that maybe something was wrong with the emulation of DOSBox X itself. It wouldn't explain the problem with the framebuffer driver, but still, there could be several problems. And I definitely encountered some weird behavior. Beyond trying DOS games, I also gave a quick shot to running early Windows 95-98 games, and so I installed Windows 98 and tried Unreal Tournament. This is what you see running here. In retrospect, I should have used Windows 95. It's lighter and the Raspberry is a bit underpowered. But the point is, it's running. Sometimes. Depending on which option for the emulation core I pick in the DOSBox X option menu, sometimes the card would not even be detected at all and refuse to initialize. But the suspicious part is that if I try an unmodified DOSBox X using the stock Voodoo 1 software emulation, I would also have those same initialization problem. Issued PCI accesses are dependent on the emulation core option, and that shouldn't be the case. Something fishy is going on there. This video is already getting pretty long, so I will stop my rambling there. I will continue to run some testing, and if I make any significant discovery, I will either post them in a pinned comment or make a follow-up video. If you have any theory about what's going on or some suggestion, post them in the comments below or ping me on the 1BitSquared Discord in the oldskool channel. I will put a link in the description. As I alluded to earlier, on my side, I might end up trying to build a PCIe and or PCI bus analyzer to see exactly what's going on. So if you're interested in hearing more about that, let me know as well. That's it for now. I hope you found this video interesting and informative, or at least entertaining. If so, please leave a thumbs up and subscribe to the channel if you don't want to miss any of the other random tech stuff I post about. And I will see you in the next one. Bye.